Hi everyone, this is Dr. Sushmita Yadav. Welcome once again to my channel Orbital. As you know, we are running a series of the stereo isomerism. Under this, we have already completed geometrical isomerism. If you haven't seen the video, please visit the playlist and watch all the videos of the geometrical isomer. And in this lecture, we are going to start the optical isomerism. What are the conditions for a molecule to be followed to be optically active? What are the types of the optical isomerism, mandatory requirement? Every minor detail we will study. So first of all, what are the optical isomers? Optical isomers are the compound which can follow the following optical requirement and show the change in the PPL. When the PPL is passed through their solution or gaseous mixture, then it will rotate the PPL. Now what is the PPL and how the changes occurs to be optically active for a compound? I will show you every detail here. So first of all, what is the PPL? PPL means this is simply plain polarized light. Plain polarized light. This is called PPL. How do we form the PPL? For example, this is a light source. This is a source of light in which, for example, this is a white light source in which all the oscillations we can see in the different directions. Then it is having, that means it is having the rays in all the directions. When such a white light is allowed to pass through a slit, slit is a thing that works to cut down all the rays except one direction. So all the radiation in the different, all the oscillations will be cancelled out. Only one direction oscillation will pass through this small hole. It is slit is something like, this is slit. Slit is something like, let's suppose you are having a cardboard in which you are piercing a small hole and keeping it in front of a bulb. Then what will happen? A small ray from the bulb will come out, rest of the radiations will be cutted down. So the same work slit is doing there. Slit is cutting down all the different directions oscillation of light. Only one oscillation or one direction is allowed to come. So such light is called PPL because it having only one plain polarized light. Okay, such light after passing through the slit, the light is called PPL. Means it is having oscillations only in one plane. When a PPL is allowed to pass through the solution of a optically active compound, solution of compound, and if this compound is able to rotate the PPL either clockwise or anti-clockwise, then it will say that the solution of this compound which is present in the solution is able to show optical isomerism. For example, your PPL is rotated from clockwise or anti-clockwise. Okay? After passing through the solution. Means this was the PPL entering into the solution. When it is coming out of the solution, the direction of the oscillation is changed. Either clockwise or either anti-clockwise. So if your compound is capable to rotate the PPL when passed through its solution or gaseous form, either solution or gaseous form, both are allowed. But basically solution give the better result than the gaseous form. It is more, that's why it is more usually taken in the examples. So what is the optically active compound? Experimentally, when a white light after passing through the slit becomes the PPL and the PPL is allowed to pass through the solution of a compound, and this compound, when whatever the light is passing through this, when this light is checked, its direction is rotated with respect to earlier one. Okay, if it is rotating clockwise, then it is called D isomer. If it is rotating anti-clockwise, then it is called L isomer. Okay, so such a compound which is capable to show PPL either clockwise or anti-clockwise is called optically active compound, and it will always exist in the two isomer. One isomer will rotate the PPL clockwise while the another one will rotate to the anti-clockwise. Correct? So a optically active compound is the compound which rotate the PPL either clockwise, capable to rotate the PPL either clockwise or anti-clockwise. Is called optically active compound. And optically active compound are able to show optical isomerism. They always have two isomers, which will rotate the light in clockwise while the another will rotate to the anti-clockwise. Okay, now optical isomers we will take here. D isomer and L isomer. Small d or small l. D isomer and L isomer. D isomer means the isomer which rotate PPL to clockwise, while L isomer which rotate PPL to anti-clockwise. Okay, and practically when we are having the two isomers of a compound, or when we found which the compound is capable to show optical isomerism, then definitely it will exist in two forms. But practically we cannot say that, cannot say without doing experiment that out of the two isomer which will be D, which will be L. It is an experimental thing. Without experiment or by seeing the structure, nobody can judge that which isomer will be showing the D or L. But it is much sure when there are two isomers, then definitely one of the isomer will be D out and other one will be L. Okay. So now let's take what are the requirements for a compound to be optically active and to show optical isomerism. So I think the definition is clear to you. I am revising once again. When a compound is capable to rotate the PPL either clockwise or anti-clockwise when passed through their solution is called optically active compound, and they always exist in the two forms, D form and L form. D form is the isomer which rotate PPL to the clockwise, L form which rotate the PPL to the anti-clockwise. Okay, and D and L identification is thoroughly a experimental thing. Without doing experiment, nobody can tell you which isomer will be D, which will be L. But it is much sure that out of the two isomer, one will be D, another one will be L. Okay, so let's take what are the mandatory conditions for the compound to be optically active and to show optical activity. And for a molecule to be optically active, one very essential requirement is that the molecule must not be symmetrical. That means unsymmetry is the reason, or unsymmetry is responsible for their optical activity. unsymmetrical molecule are essentially required to show optical activity. Okay? And if you are having a symmetrical molecule which is having either POS or COS, will never show optical isomerism. So being unsymmetrical is a requirement for a molecule to be optically active. So here, before going in detail, I am going to take another point over which direct question have been found in the exams. Chiral center. What is the meaning of chiral center? I am not saying chiral carbon, I am saying chiral center. So chiral center is an sp3 atom. Chiral center is an sp3 atom having 4 different atoms or groups. And if this sp3 atom is the carbon, then it will be called chiral carbon. Okay? For example, if I am taking carbon and there are the 4 different groups, then it is called chiral carbon. But it is not essential that every time carbon will be there as the chiral center. Your chiral center may be the carbon or may not be the carbon. Generally, along with the carbon, we have found the nitrogen. Tertiary nitrogen is also a chiral center. Okay? So, I'll give you some examples to find out the chiral centers and to check the chirality in the molecule. Okay? For example, yes, how to check how many chiral centers are there? How many chiral centers are there? First of all, always search for the sp3 atom. Any sp2 atom, no need to check the chirality for that. For example, in this molecule, this is a sp2 carbon, this one is also a sp2 carbon. So no need to check whether it is having substitution as well. It will not show any kind of chirality. I need only sp3 carbons or sp3 atom. This is sp3, but here are the 2 hydrogens are present. So out of the 4 bonds, 2 are same, so no need to check for the chirality. Here are again it is sp3, but with the 2 hydrogens, no chirality. And here is the carbon who is having 1 hydrogen, 1 methyl, one side this ring and one side over the ring. I already told you how to check the symmetry of the ring. Because the ring is unsymmetrical, one side methyl, one side this group is attached. So for an unsymmetrical ring, it will be expected it is having the 2 different groups. You can consider on this bond, this ring is attached, numbering from this side. On this bond, the ring is attached, numbering from this side. And in both the cases, you will get the different numbers for the same groups present on the ring. So that means the ring is different for the different bonds. Correct? So this carbon is a chiral center. So one chiral center is there. Another one, these carbons are not chiral. This is not chiral. This is also not chiral because it is having 1 hydrogen, but it is sp2. So for, I already told you, for the sp2 or sp hybridized, no need to check. Just go straight for checking sp3. Now, this carbon is having 1 hydrogen, 1 nitrogen, tertiary nitrogen group, one side this and one side this methyl. And definitely they are going to be symmetrical or unsymmetrical. You can check by doing numbering. So let's do the numbering and find out whether it is symmetrical or unsymmetrical. How to do? With respect to this, this is 1, 2, 3, 4, 5. Okay? And this one will be your. Now, do the numbering from right side, left to right also. 3, this is 4, and this is 5. Same group are getting the same numbers. This is 2 or 4, this is 2 or 4. Double bond is double bond is getting the different numbers. This is 1, 2, third carbon, and this is 1, 2, second carbon. So this is unsymmetrical with respect to the double bond on both sides. The distance is not equal. That's why this carbon is going to be chiral again. So 2 chiral centers we have got, 2 carbons. We must say chiral carbons we have got. Okay, now check for the nitrogen. This nitrogen is having one bond attached with this whole ring, another bond with methyl, third bond with ethyl, and the fourth hybridized atom is hybridized orbital is having the lone pair. So all the 4 are different here, so this is also chiral. So how many chiral centers are there? Total chiral centers in this molecule, chiral centers are 1, 2 and 3 chiral centers, and out of that how many chiral carbons are there? So be careful whether they are asking for chiral carbon or chiral center. Out of the 3, 2 are the chiral carbon, another one is the chiral nitrogen. Okay, so maybe in the example given you in the entrance, they must ask the chiral center. In that case, you need to check all the sp3 atom, whether it is carbon or whether it is non-carbon. Generally, nitrogen will come in this section. Okay, if they are asking chiral carbons, then go for only the carbon atoms which are sp3 and having the 4 different atoms or group. If you are not able to assign the symmetry of the ring on the 2 bonds of the carbon, please go through the videos of the geometrical isomerism. In that I have explained thoroughly how to find the symmetry of the ring or how to find the group on the ring if attached to a center, whether double bond center or whether here to the chiral center. Rules are going to be same. Now let's take few more examples and find out the chiral centers in all that. For example, I am giving you this one. So let's do it quickly. Okay, I'll give you some more examples. Let's solve all these. Yes, in all the 3 examples, we will check how many total chiral center are there, and out of the total, how many carbons and how many nitrogens are there. So here, these 4 carbons, this one, this and this, these are sp2 carbons having the double bond. So no need to check. Only this and this we are going to check for the chirality. Here are the 2 same group, hydrogens are present, so no chirality is there. Here over the ring, 1 hydrogen, 1 methyl, and if you find out the ring, it's going to be symmetrical in both the directions. Okay, so your ring is also not capable to show any optical or do not have any chiral centers. Okay, this is also not the chiral center because the groups over the ring are going to be the same or occupying the same locations or doing numbering from left to right or right to left. That's why it is having no chiral center. So please don't bother about that, like it is having any chiral center. Similarly, we are having this one, only 1 double bond. Okay, so these 3 carbons are also sp3 hybridized, but there are the 2 hydrogens, so no chirality. Only possibility is here because these 2 carbons are sp2, no need to check. Here is 1 hydrogen, 1 methyl. Now check your ring. Ring is symmetrical or unsymmetrical on going left to right and right to left. If we are doing numbering, the location for the double bond is not going to be the same on both sides. So that's why this carbon is chiral in nature. So it is having one chiral carbon. Okay, one chiral carbon or only one chiral center, which is the carbon only. Correct? Now here if we check, this is also sp3, but here are the two hydrogens present, so no need to check for this. Here in this case, one hydrogen, one methyl, one hydrogen, one methyl. So check for the chirality one by one. Go for this. This is sp3 hybridized carbon having one methyl and one hydrogen. And for the ring, same rule as we did in GI. Go clockwise and anti-clockwise, similar group. If getting the same location both the sides, then it is symmetrical, otherwise unsymmetrical. Definitely it is going to have the second location if we are going clockwise, anti-clock number 1 location. So definitely it is going to be your chiral. And similar situation on this side, it's going to be chiral again. So here are the two chiral carbons, or a total of two chiral centers, which are only the carbon. Now let's take this molecule. In this molecule, do not check this ring because it is an aromatic ring, and in aromatic each carbon is sp2 hybridized. So this is of no use. So for the sp2 we are not going to waste the time. So just go for this carbon. This is having two hydrogens, so definitely not going to be chiral. It is having two bonds having same atom, so again not going to be chiral. This carbon is having one hydrogen, one methyl, one side this complete group, one side this complete, and you can easily identify the groups are locating the different positions. That's why it will be one chiral center, and definitely this is also one ethyl, one methyl, one side this side of ring, one side this side if we rotate. Definitely different. So here again the two chiral centers, which are the carbon only. Okay, I'll give you one more example. Just solve in this way. It doesn't take time. If your concepts are very clear that all the sp2 and sp you are not going to touch, no need to waste the time with that. Just check the sp3. If rings are there, then definitely go for the rules that we discuss in the Symmetrical isomerism and find out the chirality over the carbon or any other center. Now let's take some example to count the chiral centers or chiral carbons. So for example, in this molecule you can see all are these having, all are sp3 hybridized, but you can see they are having more than one same atoms. Those are hydrogens. So only the hope for the chirality is there with the nitrogen, because this carbon 3 hydrogen, this carbon 2 hydrogen, this is again 3 and 5. So here, if we check the nitrogen carefully, it is the ethyl group, correct? This is also ethyl group, only my presentation is different. Here I am writing C2H5, here I am writing CH2CH3. This is CH3. So this group is different, lone pair is different, but these two groups are gonna be same. So that's not going to be chiral in nature. Okay, so carefully watch the molecule and then decide the chiral center. So there is chiral centers are 0. Now second one. In the second one, if we check carefully, first check this carbon 2 methyl, same group, no need to check further. This carbon 1 methyl, one side this complete group, but rest of the 2 valencies would be having the hydrogen. So definitely not gonna be chiral in nature. So now come to the next one, check this carbon. It is having 1 ethyl, 1 isopropyl, one side this group, and the fourth bond is hydrogen. So is it chiral or not? Yes, it's gonna be chiral in nature. So we are going to put a star because this is the presentation for the chiral center in the compound. If star is given, that means it is the chiral. Okay, now check the next carbon. This carbon is having 1 methyl, one side this complete group, 1 chloro, and definitely the fourth one will be hydrogen. If not mentioned, that is the hydrogen only. So it's going to be chiral again. So there are two chiral centers which are the carbons only. Correct? Now check in this one. Definitely these ethyl or methyl are not going to be chiral, having more than one hydrogens. Only hope is there. So this carbon is having one methyl, one OH group, and definitely the fourth one is hydrogen, so it's going to be chiral. So it is having one chiral center. Correct? Now in this case, if we check one by one, the corner will not have, because they are having multiple number of hydrogens. Just go for the second one. This is having one methyl, one side this complete group, one side chloro, and the fourth will be hydrogen. So definitely it is the chiral. Now similarly here, if we will see one side ethyl, one side this group, one side chlorine, and another one will be hydrogen. So there are the two chiral centers which are the carbons only. Correct? In this case, this is ethyl, this is ethyl. So two same group are there, no need to check further. So it is having zero chiral centers. Correct? Now in this one, let's be quick. This is aromatic, so no need to waste time over it. Go for this one. This is having one methyl, one side this ring, one side this ring, and the fourth bond will be hydrogen. That's gonna be chiral. Correct? Now this carbon, this is also sp3 carbon. One side this ring, another side this portion, third side this ring, and the fourth gonna be hydrogen. It is also chiral. Now this one, this is also same story like this. It's also chiral. You can check as I am checking here. Now check for this one. This is one methyl, one side this portion of ring, another side this part of ring, and the fourth will be your hydrogen. It's gonna be chiral again. Now coming to next. In the next ring, these two carbons can't be the chiral because these are having the double bond sp2. Check this one. This is having the two hydrogens, so no chance of chirality there. And now going to the next one. Here, one side this group, one side this portion of ring, another side this portion, so it's going to be chiral again. Now come to the nitrogen. Okay, let's go upside first. Move to this carbon. This is having one methyl, one ethyl, one side this whole ring, and another one will be hydrogen, so it's going to be chiral. And this one methyl, one ethyl, one side this whole portion, one lone pair. It is also chiral. Okay, so how many chiral centers are there? Total 1, 2, 3, 4, 5, 6, 7. 7 chiral centers. Out of that, chiral carbons are 6 and rest is the chiral nitrogen. Chiral nitrogen is 1. Got it? Now, this example is very special. Here, you can see your carbon, nitrogen is sp3 having the 3 different bonds or groups. One methyl, one ethyl, one ethene, and one lone pair. It is chiral, but it is not chiral actually. Why? Because you can see there is the resonance. That means the lone pair is delocalized, and when it is delocalized, then it is not present all the time over the nitrogen. So that's why it will not be considered for the chirality in the molecule. So even though this nitrogen is sp3 following all the conditions to be chiral, but due to being resonance, the lone pair is sp3 nitrogen, but lone pair is delocalized. So be careful if this kind, therefore no, not chiral. So if this kind of the example is given or some of the bond are showing this kind of property, so please do not consider the nitrogen as chiral center. Correct? And one more thing important about the chiral center. Generally, it is found, remember this as a rule, Generally, experimentally it is found the compounds having one chiral center are always optically active. So we can write it as a rule. Compounds having one chiral carbon why I am writing carbon, I will explain you, are optically active and always form D and L isomer. Optically active and show optical isomerism and shows optical isomerism, means they will always form D and L isomer. For example, lactic acid. What is lactic acid? 1-methyl, 1-OH, 1H, and what is the another group here? I think ethyl. Okay, let's take it for an example. What the lactic acid? Let's take it as a general example. In this example, we can see clearly the carbon is chiral and the molecule, this is your chiral center. The carbon is having the 4 different atoms of group, so it is a chiral center. So here, due to being chiral and it is the only chiral center in the molecule, this compound will be optically active and will show 2 isomers which will be mirror image of each other. That means we can write the another isomer. Let's suppose this is the mirror and another isomer of this compound will be shown like this. Okay, so in this compound you can clearly see out of these two, one will be D isomer, another one will be L isomer. But definitely I told you earlier that we are not sure which one is the D, which one is the L, but we are very much sure out of that 2 isomer, one will be D, another one will be L isomer. So by your comfort you can write D isomer to 1. But without doing practical, we can't tell which one is actually D. But we are sure one is D, one is L. So you can write any one of them is the D, any one of them is the L isomer. Okay? So the point is clear to all of you. If your compound is having only one chiral center, then it will be definitely optically active and will show optical isomerism. These isomers are called enantiomers of each other. They are mirror images, non-superimposable to each other. Okay? Now, one more thing here, very important regarding the nitrogen. Because we have seen nitrogen can also be the chiral in nature. But nitrogen, okay, I'll give you in writing. Nitrogen, sp3 nitrogen can be chiral centered, but do not show optical isomerism. Means, let's suppose in a molecule only one chiral center is there. Let's suppose if I make it chiral, here I am attaching one more group. If I am making this carbon as a chiral, this nitrogen as a chiral center, but this is a chiral center, but not showing the optical isomerism. So nitrogen do not show optical isomerism even though it is chiral. So ultimately these two things you need to remember when you are doing the example. But here from this point, one thing is very much clear, that to be chiral in nature, having chiral center is not a essential or mandatory criteria. Otherwise, why the molecule with nitrogen are not chiral? It should also be the chiral. That means there are some other conditions which are required for the molecule to be optically active in nature. That we will discuss in the next lecture. Thanks for watching. See you in next class.